Hello, grade 12 student. In this presentation, we're continuing what we have started before about our chapter nervous system, and this about the function of neuron. Here we move to document 3 about the nerve impulse and the action potential on our book on page 187. So let's move to the nerve impulse and the action potential. As you know that action potentials, they are signals that arise from the rapid triggering of the neural impulses. So we have a triggering, or we have stimulation of the neural impulses that propagate along the nerve fibers. So what are the characteristics of the nerve impulse? How does it propagate? Characteristics of the nerve impulse and nerve fiber. Here we have an isolated nerve fiber is subjected to stimulation of increasing intensity, as we have discovered before in our lectures number 1. So here we have stimulation number 1, stimulating electrode S1 and S2, and recording electrode R1 and R2, and they are connected to oscilloscopes. Here we have the writing membrane potentials. So we have I1 and I2 and I3, the thing causes an action potential. I4, it causes an action potential. I5 and I6. As you see here, all the action potentials, they have the same amplitude. They have the same amplitude. Here, in the second experiment, the nerve fiber is subjected to only one stimulation of an intensity above the threshold. So this will cause an action potential. The response is recorded by 3 oscilloscopes with recording electrodes placed at different distances from the stimulating. As you see here, all of them, they have the same amplitude. And here we have the distance between them. Okay, so if you want, for example, here to interpret, so after the interpreting of the experiment at document B, which is the part 1 in the probing the document. So interpret, so after applying stimulation on the nerve fiber, 3 action potentials, they occur having, all of them, they have the same amplitude. All of them, they have the same amplitude, all of them. So this indicates that the nervous message is conducted in the nerve fiber with amplitude which is constant of its action potential. The amplitude is constant. Characteristic of the nerve impulse in a nerve. A nerve is made up of different type of axons. They are myelinated or non-myelinated, of small or large diameters. The nerve carries the nerve impulse at different velocities as shown in document D. In the body, the non-myelinated nerve fiber are twice as much as the myelinated ones. So here we have variation of the speed of conduction of the neural impulse in certain nerves. So average diameter, if the diameter is 13, for example, the average speed is 75. When it decreases to 9, the speed decreases to 55 meters per second. When it decreases to 3 micrometer in the deep muscle receptors fibers, which is sensitive to pressure, the speed decreases to 11 meters per second. And then when the average diameter decreases to 0.5, here it decreases to 1. So here, as we see, the average speed of the propagation is decreasing whenever the average diameter of the nerve fiber is decreasing. So this indicates that the average speed is directly proportional to the diameter of the nerve fiber. So using the same setup as shown in same setup as that of the nerve fiber of document A, stimulation of increasing intensities, they were applied on the nerve. The recordings obtained by oscilloscope O1 are presented in document E. In the second experiment, the stimulation with intensity above the threshold is applied. The recording electrode R1 is displaced on the nerve in such a way that each time we change the distance of the stimulating electrode, the obtained traces are shown in document E. So as you see here, distance between, whenever the distance is, for example, 15, we have an action potential, 70, 110, and stimulations, and it occurs with time. So here, I1 and I2 and I3, there is no action potential. I4, we have the first action potential. So as we move here to document E, part 2, different distances. Here, different distances we have. Whenever the distance between the S2 and R1, it was 15 millimeter, we have only one one action potential is recorded. But as the distance increases from 15 to 10, we have two action potentials were recorded, two peaks were recorded. Okay, and this the first action potential is recorded about after 3 milliseconds of the stimulation, and the second is recorded after about 6 or about 5 or maybe 5 or 6, 5.6, 5.5 or 6 millisecond. So we can say that the nervous message you are conducted at two different speeds. Either the nerve contains two different kinds of the nerve fiber. Maybe the first one is myelinated or have a large diameter, that's why it's faster. And the second one, maybe it's non-myelinated or maybe it has a small diameter. That's why the message will be conducted in a slower manner. So the peak of the action potential recorded at time equal 3 seconds is higher. As you see here, the peak is higher than the one recorded at time equal 6 milliseconds. So the nerve fiber that conduct the message faster, they are more frequent than the fiber that conducts the message, which is the slower. So they are more frequent in this message. Okay, propagation of the nerve impulse in a nerve in a fiber. If you experimentally stimulate an axon at certain point, the produced action potential propagates from the side toward both extremities. Meanwhile, in the body, the action potentials, they take place at one of the extremities, and the nerve impulse propagates in the direction of the other extremity. In a given site, as the polarity of the axon membrane is reversed to the action potential, so the attraction between the positive and the negative changes in the neighboring zone produce a local current that depolarizes the next zone that is not yet depolarized, hence making it more permeable to Na+. Then the depolarization of this segment produces at this place an action potential that depolarizes the segment that after it, and so on. So the action potential moves step by step along the axon. We say that it propagates following this neural impulse. The K+ ions they cross membrane to the outside. Thus we have nerve repolarization as shown in document F. So we have nerve repolarization going back to the polarity. In a given site, for a fraction of millisecond and at the moment of the creation of an action potential, the nerve fiber is unexcitable. It's said to be in a period. This period is called a refractory period. So the depolarization obtained at a certain zone extend in the neighboring zone. During this time, the zone that has depolarized polarizes again, and in the period which is called the refractory period, this one will prevent the backward depolarization, which causes the message to be unidirectional. So this is very important for the unidirectional propagation of the nervous message. This is why the action potential, as I said, does not move backward, and its propagation is done in one and only one direction. So here, in a myelinated axon, depolarization that results from an action potential at the nodes of Ranvier, there are the spaces that exist between each myelin. They spread inside the axon to the next node where it starts a new action potential. So the action potential jumps from one node to another. This conduction is called saltatory movement, as we said before. Okay, it's called a saltatory movement. So by the interpretation of document paragraph 1, pick up the characteristics of the nerve impulse. We said that the nerve impulse is conducted with constant amplitude, as we said before. So after applying stimulation on the nerve fiber, three action potentials having the same amplitude, they are recorded by the three oscilloscope. This indicates that in the nerve fiber, the message is conducted with constant amplitude of its action potential. Here we move somehow to physics. They said calculate the velocity in part 2. Velocity equal distance over the time. Distance in centimeter, to be in meter, it's 10 to the power minus 2. Since it's 1 centimeter, so 1 centimeter is 10 to the power minus 2 meter. And 10 to the power minus 3, it represents 1 millisecond, so it's 10 to the power minus 3 seconds. So the speed is 10 meter per second. Number 3, they said the comparison between the speed of propagation of the nervous message. For the myelinated nerve fibers, the diameter of the nerve fiber decreases from 13 micrometer to 3. The average speed of propagation, it decreases from 75 to 11. What does this indicate? This indicates that the average speed is directly proportional to the diameter. So as the diameter increases, the speed will increase. As the diameter decreases, the speed will decrease. So this is the first factor that affects the speed of the propagation of the nervous message. It's one of these is the diameter. For nerve fiber having diameter 3 micrometer, the average speed it was in myelinated fiber it's 11 meter per second, which decreases to the non-myelinated nerve fiber to 2 meter per second. So here we have another factor. Myelin accelerate. What the meaning of accelerate the nervous message? It makes it faster. So here we have till now 2 factors that affect the propagation of the nervous message. Speed, we have myelin, and we have diameter. So deduce 2 factors affect the speed. Number 1, myelin. Number 2 is diameter. So as you note here, as temperature increases, the speed will increase too. Let's move now to part 5, talking about the document about the S2 and R1 stimulation and recording. When the distance between them was 15 millimeter, after applying a stimulation, an action potential is recorded. So as the distance between S2 and R1 is increased to 110 millimeters, and after applying a stimulation, 2 action potentials with 2 different peaks are recorded. First one is recorded after 3 milliseconds of applying the stimulation, while the second one is recorded after 6 milliseconds. So the nervous message here is conducted at 2 different speeds. What does this mean? This means that the nerve contains 2 kinds of nerve fibers. The first kind, maybe it's myelinated and have a large diameter and conduct the message faster than the second one, which may be non-myelinated also here or maybe myelinated, maybe it has large diameter also, or one of them, or maybe it's non-myelinated and or having small diameter and conduct the message in a slower manner. That explains that the peak of the action potential recorded at time equal 3 milliseconds is higher than that recorded at time 6 milliseconds. So the nerve fibers that conduct the message faster are more frequent, and the fibers conduct the slower message. So to talk about depolarization. Depolarization obtained at the certain zone extends in the nerve zone. During this time, the zone that has depolarized polarizes again and is in a period is called refractory period. This period prevents the backward depolarization, which causes the message to be unidirectional. It is always propagating in one direction. Okay, so now let's move together to document 4. Document 4, sensory receptor and the nerve impulse, page 190. Sensory receptors and the nerve impulse. Here we have the experimentally, it's possible to stimulate each point of a neuron or of an isolated nerve to obtain a nerve impulse. But in vivo, the genesis of these impulses is done by specialized neuron structures. What are these structures? How is an impulse triggered at the level of these structures? So let's start together step by step. Different types of receptors. Sensory receptors, they are nerve structures specific to a given stimulus. According to their location, the various sensory receptors are classified into 2 large groups. External receptors that receive information from the external medium or external environment, like the light, sound, and others, and internal receptors that receive information from the internal medium, from our body. Receptors also, they are classified according to the type of energy of the stimulation, as shown in document 8. For example, the one that Responses to the touch, pressure, and stretching, they are called mechanoreceptors. Sensory organ, maybe it's the skin, muscles, and the vessels. Temperature variation, they are called thermoreceptors. The sensory organ is the skin and the tongue. Light type of receptor is called photoreceptor, mainly through the sensory organ, the eye. Pain stimulation, high pressure and temperature is called nociceptors. They are present at the sensory organ of the skin. Transported molecules, they are called chemoreceptors in the tongue and the nose. From sensory receptor to action potential. The function of receptors is to convert the different forms of energy into electrochemical energy, or in a simple way, action potential, AP, and transmit it to the nerve centers. Pacinic corpuscles, they are touch receptors. Touch receptors that are sensitive to variation of pressure. So the pacinic corpuscles, they are, as I said here, they are mechanoreceptors. Okay? Each corpuscle consists of unmyelinated sensitive nerve ending surrounded by a capsule made of concentric layer of connective tissue. The nerve fiber joining the corpuscle, this corpuscle, to nerve center is a myelinated fiber. So, pacinic corpuscle, they are mechanoreceptors and they are excitorreceptors. So, isolated pacinic corpuscles, let's see here, with its fiber, they are placed in a physiological solution. 3 electrodes, they are inserted at 3 different points of the nerve fiber, R1, R2, and R3. And appropriate system allows the application on the capsule of a pressure of intensity above the threshold. It's called supraliminal intensity. Document B represents this setup. On the screen of the oscilloscope, recordings are obtained from 3 different points. So stimulus, we have stimulus of the pressure, 10, and so on. So before exerting the pressure on the pacinic corpuscle, the resting potential, generating potential, and the potential recorded in the nerve fiber, they are equal to minus 70 millivolt. Okay? After applying the pressure of 10 gram per centimeter square for about 2 seconds, okay, so for about 2 seconds here, we have, so on the pacinic corpuscle, the receptor potential increases to about 0 and then decreases slightly to its initial value. And after 2 seconds of applying the pressure, they return to the initial value, as I said. During this time, a train of potential of the amplitude 100 millivolt. This one is observed in frequency decreasing with time. So decrease to 100 and decrease with time. Also, a train of action potential is recorded in the nerve fiber with a frequency decreasing with time. As I said, this indicates that for the supraliminal intensity of stimulation, the receptor potential is local, is instantaneous, is occurring and at instant, and disappear with distance, where generated area produces a depolarization followed by a potential. This generating potential causes the elaboration of a train. This is called a train of action potentials that propagates. Okay? So before applying this, for applying a pressure, the receptor potential is equal to minus 70, as we said. So the potential in the nerve fiber is equal to minus 70. After applying of pressure, which is about 0.5 gram per centimeter square, 0.5 gram per centimeter square, the receptor potential increases to minus 50 millivolt. So increases to minus 50 millivolt. The receptor potential. We are talking about the recepting potential. So, and then decreases back to minus 70 millivolt in 2 seconds and remains below the threshold of depolarization. So no action potential. So this indicates that the pressure 0.5 gram per centimeter square is ineffective, since it doesn't cause the elaboration of the action potential in the nerve fiber. After increasing this one to the pressure of 1.5, so we increase this to 1.5 gram per centimeter square, so increase to about 1.5. So the receptor potential, as we said, the receptor potential increases above the threshold and reaches minus 40 millivolt, and then it decreases to minus 70 again in 2 seconds. This leads to the appearance of the action potential in the nerve fiber with a frequency that decreases with time. Here we move to this indicates that the pressure 1.5 gram per centimeter square is effective above the threshold and causes increase in the receptor potential above the threshold of depolarization, which leads to the elaboration of action potential in the nerve. So as we increases to 2.5 gram per centimeter square, so as we increases to 2.5, the level of the action potential frequency higher than that obtained and increased to about minus 30 millivolt, but the amplitude of the action potential, it remains the same. This indicates that the pressure 2.5 is an effective one. It causes an increase in the intensity and also an increase, in the intensity, causes an increase in the frequency, but not in the amplitude. This explains that the nervous message is coded or it's modulated or is conducted according to frequency and not according to the amplitude of the action potential. Here, the difference is the frequency. The amplitude is approximately constant. Okay, so here we saw what type of receptor is the presenocorpuscle. We said that the presenocorpuscle is a mechanoreceptor and it's an X-ray receptor. Compare the electrode, the recording obtains on document B, and then state the characteristics of each one. We said we compare these, and in a fiber, a nervous message is modulated in frequency and not in amplitude. Justify the statement. We justify this statement according to this. All of these notes already we have taken this before, but this note is during this application. Presenocorpuscle is a mechanoreceptor and X-ray receptor, as I said. Number 2. That said, you have to compare the recording obtained in document B, then state the characteristics of each potential recorded before exerting pressure on the presenocorpuscle, the receptor potential, generating potential, and the potential recorded, it's equal to minus 70 millivolt. After applying a pressure of 10 gram per centimeter square for 2 seconds, the receptor potential increases from 0 millivolt, then decreases slightly to its initial value after 2 seconds of applying the pressure. During this time, a train of potential, as I said, train of potential of amplitude 100 millivolt is observed, with frequency decreasing with time. So also a train of action potential is obtained in the recording nerve fiber with frequency decreasing with time. So this indicates that for supranominal intensity of stimulation, the receptor potential is local, instantaneous. So you have to pay attention to this local, instantaneous, and disappear with distance, whereas the generating area produces a depolarization followed by a potential. This generating potential causes the elaboration of a train of action potentials in the nerve fiber that propagate. Number 3, they said a nerve fiber is modulated in frequency and not in amplitude. We explained this, that as the intensity increases, the first one, it was ineffective. So pressure 0.5 gram per centimeter square was ineffective. So, and doesn't cause the elaboration of an action potential in nerve fiber. While when it increases, the 1.5 is effective. It's above the threshold. It leads to elaboration of the action potential. While 2.5 gram per centimeter square is effective, it causes an increase in the stimulation. It causes the increase in the frequency of the action potential, but not in the amplitude. It causes increase in the frequency. Pay attention to this. So, therefore, the nervous message in nerve fiber is conducted or it's modulated according to the frequency of the action potential and not according to the amplitude. This is a very important note. Thank you guys. Hope you enjoyed this video. Bye bye.